Okay, cis-trans and easy isomerism and its effect on physical properties and chemical properties. Not a major portion of this topic. Mostly it's about identifying this isomerism and possibly naming it, but they can have some small questions about its effect on different properties. So if we look at a couple of examples, you can see that cis-trans isomerism could affect polarity because of that orientation. If you have polar bonds, right, like the bond between carbon and bromine is a little bit polar. You can see in this example, both bonds are oriented up in the cis orientation, whereas in this one, they are oriented in different directions. Now, certainly in the bottom one, the trans example, there is a bit of a net dipole in this direction. So there would be a little bit of negative charge to that end and a little bit of positive charge to this end. However, it's not going to be as much as in the top example, where the two atoms are oriented up and they can combine their polarity and make a bigger dipole. So you can have slight differences in polarity, which can lead to differences in dipole-dipole forces, depending on if you're cis versus trans. Cis versus trans can also affect London forces. The classic example of this is with cis and trans fats. Fatty acids have carboxylic acid groups or carboxyl groups, and then they have long fatty tails that are just hydrocarbon, just C and H. And unsaturated fatty acids have carbon-carbon double bonds. Normally, unsaturated fatty acids are in the cis orientation. So a normal unsaturated fat would look something like this. This is a monounsaturated fat. There's one carbon-to-carbon double bond. And the carbon chain, part of it, comes out on the same side of that carbon-carbon double bond. And that puts a kink in the tail, versus a trans unsaturated fatty acid has the carbon chain coming in across from one another in those opposite trans orientations. And that makes the chain much straighter and a lot more similar in structure to a regular old saturated fatty acid. And so these ones, because they are straighter, they have greater surface area, and that makes them have greater London forces. So they have higher melting points. And so unsaturated fatty acids and trans fatty acids tend to be solid at room temperature, whereas cis unsaturated fatty acids tend to be liquids and makes them into oils. So it's that idea of straightness affecting the surface area overlap between neighboring molecules. And cis-trans isomerism can also affect the ability to hydrogen bond between molecules. So this is a cis-but-2-ene-1,4-dioic acid versus the trans example. So you've got these, it's a 4-carbon chain with 2 carboxyl groups on the end. Now the cis molecule, the groups are oriented towards themselves, whereas in the trans one, they're oriented across from each other. So in the cis one, there's hydrogen bonding inside of the molecule, depending on how it's oriented. If the OH group is drawn over here, instead of the C to O double bond, and the C to O double bond is drawn there, you could have some internal hydrogen bonding between the groups, but that doesn't really help the boiling or melting point because we're looking for hydrogen bonding between molecules to raise the boiling point or the melting point. And the trans example has more locations for intermolecular hydrogen bonding. So because of that orientation, so the orientation in trans has greater ability for H bonding between molecules. So that's the intermolecular force, whereas the cis one can do that to an extent, but because all of the hydrogen bonding groups are sort of pointed in one direction, kind of inwards towards itself, it can't form as many hydrogen bonds with its neighbors, so it overall has weaker intermolecular hydrogen bonding. So we would expect the one on the left to have a lower melting point or boiling point compared to the one on the right, which has stronger overall hydrogen bonding with its neighbors. We can actually look at the same example molecule, cis-trans, and this is the main distinction on chemical properties that they point out. It's just one random example. I wouldn't really expect it to be on your IB exam. But simply to be aware that when we have these differences in orientation, it can also change how things behave chemically, meaning how they react. So the example here is that trans one with the 2 carboxyl groups is pretty much behaves normally. As you warm it up, it goes from being a solid to a liquid, so it just melts. So that's what you would expect of a solid. As you warm it up, it will melt if you reach its melting point. But in the cis example, because of the unique orientation of those 2 carboxyl groups, right, as you increase the temperature and you cause greater and greater vibration within the molecule, so you start to cause all the bonds to move, those carboxyl groups can actually start to collide with each other, and they can react with each other because of the fact that they're oriented towards each other in the cis orientation. They can't do that in the trans orientation because they're oriented in opposite directions. But in the cis orientation, as we increase the temperature, the 2 carboxyl groups react internally and actually creates this type of molecule, which they call an anhydride. And so they've undergone a condensation reaction where a water molecule has been removed and we've bound 2 things together in the process. So it's kind of a random example, but the idea of it, that depending on the orientation, cis versus trans, things oriented in the same direction versus across from each other, that can influence and differentiate how things will behave chemically, how they will react. And so this is just one example that they've chosen to highlight to show that that difference is possible.